Okay, so hi everybody. So as usual, please type your name into the chat room. I know I saw some messages in the chat room about people not getting data. So the way to make sure that you get your data is to make sure that you type your name into the chat room so that we can start. Okay, I'm just going to tell everybody in the classroom, class is starting now. Um, okay, so. Okay, great. So I want to spend time reviewing what we did last week because we covered three different topics last week, and they're all kind of small topics, but they're all kind of important. So we'll go over a homework question on each of them. And then I want to start talking a little bit about what's going to be the integral calculus. And we've been talking about what's called the differential calculus. We're not going to spend very much time on the integral calculus. We're going to have maybe two classes on it. It's not going to be the focus of our class, but it is important to say a little bit about it and what are its applications to physics and to geometry. So today we're going to see a physics application of integral calculus, and next week we'll see a geometry application of integral calculus. Okay, so once again, please type your name in so that I have a record of your attendance. And let me start with a little bit of review from last week. Okay, so last week we covered three topics, and the first topic was what's called a tangent line approximation, right? So this tangent line approximation. So we have our setup, and the setup was that f of x is a function, and it's differentiable at a point A, okay? So meaning you can take the derivative. So what we've seen from a few times about drawing these tangent lines is that the tangent line to its graph, you can write down the equation. And that equation, which we derived last time, is that y is equal to f of a plus f prime of a times x minus a. Okay, that was the definition of the tangent line. And for values of a near x, the idea is that the tangent line is a pretty good approximation to the actual graph. So the actual y value, which is f of x, is pretty close to f of a plus f prime of a times x minus a. And what's the picture here? The picture is if I have some graph that looks like this, it's my graph y equals f of x, and this is my point A here, this is my x value A, and then I draw the tangent line at A. Let me redraw that tangent line so it's more of a tangent line. If this green line here is the tangent line, so green equals tangent line, then the idea is if I take some point X over here that's pretty close to A, then if I look at what the actual f of x is, right, this is how I figure out the actual f of x. I look at the point on the graph above x and see what the y value is. That is f of x. But if I look at the value on the tangent line here, so maybe I'll make it purple. If I instead just look at the point here on the tangent line, this is going to be governed by the definition of the tangent line. So this is f of a plus f prime of a x minus a. Sorry that the writing is so small. But the idea is this green thing is the tangent line. The blue thing's the actual graph. And the point of the tangent line is that it's pretty close to the actual graph. Okay, so this is a good approximation. So what we're saying is that f of x is not exactly equal to this expression, f of a plus f prime of a times x minus a, but it is a pretty good approximation to this expression. Okay, the purple and the purple is the value on the tangent line, and the red is the value on the graph, and they're pretty close to each other. Okay, so this was the first topic that we talked about yesterday, and this was the idea of a tangent line approximation. Okay, and the nice thing about a tangent line approximation is it allows you to compute by hand very good approximations to quantities that might otherwise require a calculator. Okay, because usually this expression, if you have a good value of a, is easier to evaluate than the actual expression f of x. Okay, so this was this idea of a tangent line approximation. Okay, you can't compute the value on the curve, but you can compute the value on this tangent line, which is pretty close to what you want to get. Okay. So let's see an example of this. Okay, so let's see an example of this. So from the homework, it was use a tangent line approximation to approximate 1 divided by 4.002 without using a calculator. And then check your answer using a calculator, right? To actually get the correct answer for this, you really need to use a calculator or your phone or whatever, right? 1 divided by 4.002, you're not going to want to do this by long division. That's going to be a pain. But what's the idea here is use a tangent line approximation to f of x, which in this case is going to be the function 1 over x. Hey, we're trying to evaluate 1 over 4.02, and we know that f of 4 is equal to 1 over 4, and we know what that is. That's 0.25. That's what 1 over 4 is. What we want is f of 4.002, which is equal to 1 over 4.002. And if we wanted a decimal for this, well, we know it's pretty close to 0.25. But what is it really? That's something that we don't know. So if we go back and we look at this tangent line approximation, well, I have f of x is 1 over x. This a over here in the tangent line, this is the kind of known value. Right? So the a value that you use in the formula is a value that you can easily evaluate your function at. So in our case, the a value is going to be 4, and then the x value, so maybe actually let me write this over here. So this is going to be the known value. And then the x value is the value where we want to approximate. Okay, so in our case, the x value is 4.002. That's what we're going to want to use. Okay, so in this case, so in the tangent line approximation, we take, as we saw on the last slide, a equals 4 and x equals 4.002. Okay, so this is James's answer, and this is probably correct. So let's look at the actual formula. So the formula says that f of x is approximately equal to f of a plus f prime of a times x minus a. So what is that? Let's punch in our values. So that says f of 4.002 is approximately equal to f of 4 plus f prime of 4 times 4.002 minus 4. Right, this is I just plugged in x and a every time that they appear. Now there's one thing that, so this is what we want to evaluate. So this we don't need to do anything at all. So this here is the f of 4 is, let me get red pen, right? This f of 4 here is 0.25. 4.002 minus 4 is just 0.002. And now we have this f prime of 4. So to do that, we actually have to take a derivative, right? That's why, we're doing calculus here. We actually have to take a derivative. So what do we get with this f prime of 4? Well, f of x up here, remember, is 1 over x. And another way we could write that is x to the minus 1, right? So using the power rule, we have that f prime of x is equal to negative 1 times x to the minus 2. Or in other words, this is negative 1 over x squared. So f prime of 4 is going to be negative 1 over 4 squared, right? Because f prime of x is negative 1 over x squared. So f prime of 4 is negative 1 over 4 squared. And so what does this all come out to be? So this comes out to be 0.25 minus 1/16 times 0.002. Okay. Or another way of writing this would be 0.25 minus 1/8 times 0.001, right? I can do this because I just divided this by 2 and I also divided the 16 by 2. That's fine. And so maybe you know that 1/8 is equal to 0.125. Okay, so if you really let me just finish this up, I don't have space here. Let me just finish this up over here. So that's 0.25 minus, well, if 1/8 is 0.125, then I multiply that by 0.001. That means I have to move the decimal place over by 3. So that's going to be 0.000125. And if you write this down, you get exactly what James wrote in the chat. You get 0.249875. Okay. Okay, so the point is, I mean, I may have done this a little bit fast, but the idea is this is all now just arithmetic that you really could do without a calculator. Okay, maybe it takes a few steps to figure out, 1/16 times 0.002, but it's just the same as 1/8 times 0.0001, so times 0.001, and this is something that you can figure out by hand if you have enough time. So you get 0.249875 as your answer for this tangent line approximation. And now, what's the actual answer, just so we can check? Let me see what happens on a calculator. If I do 1 divided by 4.002, I get a very, very close answer. The actual answer, which maybe I'll write over here. The actual answer, sorry, this slide is going to be a little overstuffed. The actual answer is 0.249875062. So this is an amazing amount of accuracy, right? I mean, 1 divided by 4.002, to actually do that would be an extremely hard computation with lots of long division and everything. And instead, with this tangent line approximation, we do what's a pretty easy computation, right? None of these quantities, the f of a, f prime of a, x minus a, none of these quantities is that hard to compute. And then you can just do the arithmetic with them, and it's not that hard. And you get an answer that's correct to 7 decimal places. So that's really quite good. 7 decimal places is about as much as you'd ever really need, right? So this tangent line approximation gives a nice way for computing functions that are evaluated at points that are close to points where you know the answer. So again, you're doing 1 over 4.002. That's close to 1 over 4. And this is going to tell you exactly how things change. All right, was there a question? I heard somebody unmute themselves. Any questions on this example? Okay, so there's kind of 2 things to take away from this. One is just getting practice using tangent line approximations, which is good. And the other thing is to get an appreciation of how this technique really gives you answers that are very close to the actual answer that you can do by hand. Okay, so you do have the power to do computations like this. And the key step to realize here is, in addition to the formula, what's the other hard part of this problem is you need to know what function to use. So when you see 1 divided by 4.002, you think, oh, it's asking me to evaluate 1 over something. And so that 1 over something, I got to plug in 4.002, but the function is 1 over x. And it's just I want to evaluate it at 4.002 instead of just at 4. Okay. Any questions on this? Okay, let's move on then. Okay, so the other topic that we did last time is called Newton's method. So Newton's method was, let's say that we're trying to solve an equation. We're trying to solve an equation of the form f of x equals 0. Okay? So your calculator can solve these equations. Wolfram alpha can solve these equations. A graphing calculator can solve equations. What does it do? What it does not do, it doesn't do what we do in high school algebra class, where it like tries to solve the equation by doing something to both sides and solving for x, the way you solve linear equations or quadratic equations or even trigonometric equations. The calculator doesn't do that because there's too many types of equations to solve like that. And so there's no way that it would have enough techniques to do it. What your calculator instead does is this kind of numerical approximation method, which is what Newton's method is. So the idea is if you have an equation f of x equals 0 and you want to solve it, you start by taking a guess that's maybe close to a solution. And then what we showed last time is that you can keep getting new guesses by doing this procedure. If x0 is your first guess, then your second guess is x0 minus f of x0 divided by f prime of x0. Then your next guess after that, if you call that guess x1, then your next guess after that is going to be x1 minus f of x1 over f prime of x1. And your next guess after that is going to be x2 minus f of x2 over f prime of x2, and so on. Okay? And eventually, if you do enough of these, it's just going to start to converge. You're going to get the same number of decimal places everywhere. So we can stop when we've achieved enough accuracy. And in most cases, you end up converging to a solution very quickly. You don't need to do very many steps of Newton's method in order to get an approximation to a good number of decimal places. Okay? And this is really like the basic algorithm of what's going on under the hood when your calculator is trying to solve an equation. Okay? So, and if you remember, I don't want to go back over the whole thing, but there was a picture of this method was if you had some equation that looked like this, and you're trying to find the solution, the idea is you start with a guess here, x0, and then you draw the tangent line coming here. This becomes your next guess, x1, and then you draw another tangent line there, and then where that goes becomes your next guess, x2, and so on. And this is how you can see that these things converge toward the actual solution. And this algebra over here is just translating this geometry into equations. So I'm not going to do that again today, but you can look in the notes from last week to see how we got these equations from this picture. Okay, so let's do an example. So let's try to use Newton's method with two steps to approximate a root of x to the fifth minus x minus 1. Right? So when I say approximate a root, what I mean we're doing is we're trying to solve x to the fifth minus x minus 1 equals 0. Right? And this is an equation that you can't solve, right, by yourself. You're not going to be able to solve this by hand. Okay? There's no easy factoring that you're going to find for this equation. You're not going to be able to just manipulate it and get to a solution. Okay? You can try, but it's not going to work. So the best we can do is try to, use this Newton's method. And so we have our initial guess is x0 equals 1. So let's remember our Newton's method formula. Newton's method formula is saying that x1 is going to be equal to x0 minus f prime of x0 over f of x0. Right? And here, f of x is just our function. It's x to the fifth minus x minus 1. And that means f prime of x is equal to, somebody want to say, just for practicing derivative, what's the derivative of x to the fifth minus x minus 1?
Yeah,
Yeah, Robert?
another one.
Yeah,
Yeah, the derivative will be 5x to the fourth minus 1.
perfect. Thank you. Yeah, that's great, right? You bring the 5 down, get 5x to the fourth, the x becomes 1, and the 1 disappears. Okay, so to get our first, we're going to do two steps of Newton's method. So to get our first guess, we're going to take 1 minus f prime of 1 over f of 1. Okay, and so what is that? This is equal to 1 minus, well, f prime of 1, if we plug in 1, we just get 4, right? Because it's 5 times 1 to the fourth minus 1, just 5 minus 1. And then f of 1, if we plug in 1 over here, we get 1 minus 1 minus 1. So that's going to be 1 over 4, 1 minus 4 over 4 minus 1. I'm a little worried this guess is not going to be a good guess. Let's see. I'm a little worried about this guess. I'm not doing anything wrong here, right? Okay, well, let's see. Let's just do it. Let's see how this works, okay? And so what are we going to get here? This is going to be 1 plus 4. Oh, wait, did I do it? That's why I did it wrong. Aha. Oh, okay. Sorry. I copied down the formula wrong. It's f of x0 divided by f prime of x0. Sorry, copied the formula down wrong. That makes much more sense. And this is f of 1 divided by f prime of 1. And so that's going to be 1 divided minus 1 over 4, which is equal to 1 plus 1 over 4, which is equal to 1.25. Okay. So this is going to be our first guess, is x1 is 1.25. Okay. So now we'll do one more step. We have that x2 by the formula is x1 minus f of x1 divided by f prime of x1. So what is this? This is 1.25 minus f of 1.25 divided by f prime of 1.25, which is equal to 1.25 minus, so what is that? That's 1.25 to the fifth minus 1.25 minus 1 divided by 5 times 1.25 to the fourth minus 1. So this let me actually do on a calculator, but the point is you can do this just on a regular calculator. You don't need a fancy equation solver. This is just doing multiplication and division, right? So 1.25 to the fifth minus 1.25 minus 1. So let me just write out what this is going to be. 1.25 minus this divided by 5 times 1.25 to the fourth minus 1. Okay, so I got that this comes out to be about roughly 1.178. I want to make sure I typed this all in correctly, but I think that should be right. 1.251, 1.25 to the fourth minus 1. Yeah. Okay, so this comes out to be 1.178. Okay, great. Okay, so James agrees with me, so that means that it's probably right, because James is always right. So we'll call it 1.178 or 1.1785. That's fine. You can add an extra decimal place if you want. And so now let's see what the actual root is. I'm going to do this in a calculator. I'm going to say solve x to the fifth minus x minus 1 equals 0. And what happens when I try to solve it? Let me put on Wolfram alpha to try to solve this. Maybe I'll share my screen to do this so you can solve these equations. Let me share my screen here. Here we are. Okay, so I'm sharing my screen for Wolfram alpha. I'm going to solve x to the fifth minus x minus 1 equals 0 in the real numbers. I press enter, and let's see, it's going to solve it. It's thinking. It's thinking for a while. That's my internet. Oh, I'm on Edge Room. Ugh. Okay. Okay, it's going to be thinking. Let me try this again. My computer seems to be going slowly. Or Wolfram Alpha is going slowly. There we are. Okay, good. So what's the real root? So if you see, this is a quintic equation, so it has 5 solutions. The first four solutions are imaginary, so we're going to ignore those. And then we have the one solution, which is real, which is 1.1673. Okay, right? So it's not exactly the right solution, but we at least got something relatively close. We got 1.1785. So we were good up to like 1 in 100. Okay, so 1.1785, 1.1673 is not so bad. And if we did another step of Newton's method, we would get even closer. Okay, so let me just stop the share here. So 1.1673, let me share my iPad again. Blah, 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 blah. Okay, am I sharing the screen? Oh, I'm still sharing the screen. Okay, great. That work? Yes, great. Okay. Wolfram Alpha, it's just the internet. So I don't know if Wolfram Alpha has its own app, but if you just open, Safari or Chrome or Firefox or whatever browser you use, and you just type in Wolfram Alpha, you can get to it. So it's called, Wolfram Alpha. Okay. Yeah. Okay, so that's 1.1785. And the actual answer we said is approximately 1.1673. Okay, so it's not such a bad approximation. And if we did one more step, we could get even better, right? I mean, what would be x3 would be equal to 1.1785 minus f of 1.1785 divided by f prime of 1.1785, right? And you could do that one more time. Maybe yeah, no, I'm not going to do that. But you could do that, and maybe I'll leave it as an exercise to you if you want to try it to see that this will get you an approximation that's even better to the actual root over here. Okay. Okay. Okay, yeah. So this Wolfram Alpha will kind of do a lot of math solving for you. And the nice thing about it is that you don't need to know any programming language. You just type in natural language what you want. See, all that I wrote was solve this equation, and it just does it. So as long as you give it a simple command in natural language, it will understand what you mean. You don't need to have the syntax of a serious programming language or anything like that. Okay. Okay. Okay, good. Any questions on this example? So I'm going to just box our final answer here, which is 1.1785, and I'll box the actual answer, which is 1.1673. Okay. All right, let's move along. So we did a third topic last time, and that was called L'Hopital's rule. And this was for evaluating limits in the form of fractions. So if we have a limit in the form of a fraction, limit as x goes to a of f of x over g of x, and this a is very general. It can be infinity, it can be a one-sided limit, it can be anything. That if the limit of the top and the bottom are both 0, or if the limit of the top and the bottom are both infinity, so that you would get an indeterminate form here, what you could do is take the derivative of the top, take the derivative of the bottom, and then triangulate with the limit. Okay? And if you can do that, then you're going to get the right answer. Okay. Sorry, Boima, did you have a question? No. Okay. Okay. Great. Okay. Great, 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 great. Okay. So this is what it is. So L'Hopital's rules formulas are usually pretty simple. Okay. So I guess I should say also, just to be completeness, just to be complete here, of course, you need that f and g are differentiable at A to make this work. Okay. Or really, really at, or really, in a neighborhood. Right? So, I mean, all that I mean is that you have to be able to take these derivatives if you want to do this limit. Okay, so let's look at an example. Say that we want to evaluate the limit as x approaches 0 of sine of 4x divided by tangent of 5x. Okay? Well, what happens if we plug it in, right? The limit as x approaches 0 of sine of 4x is just sine of 4 times 0. It's a continuous function, so we can just plug in 0, and that's sine of 0, which is 0. And similarly, the limit as x approaches 0 of tangent of 5x is tangent of 5 times 0. It's also continuous at 0. And this is tangent of 0. And that's also 0. So we get this 0 over 0, which is an indeterminate form. Okay. We get this indeterminate form over here. So we use this L'Hospital's rule. What happens, we just take the derivative of the top and the derivative of the bottom. So we need to take the derivative of sine of 4x, right? So we need to do what is the derivative of sine of, and I'll put extra parentheses here, 4x. So remember, when we're doing this derivative, this is a composite function. We know the derivative of sine of x is cosine of x. But here it's not just sine of x, it's sine of 4x. So what rule do we need to use in order to evaluate this derivative? Since we've got an inside function, 4x, and an outside function, sine. So what rule do we have to use?
The chain rule.
Chain rule, exactly, right? So Robert, do you want to do the chain rule for this derivative?
Yeah.
Mm-hmm.
Yeah, the derivative of sine of 4x will be 4 cos of 4x.
Perfect, right? So just to review for everybody, remember, you have to take the derivative of the interior function here. That 4x is becoming the 4. You're taking the derivative. And then you also take the derivative of the exterior function. And that's why the sine is becoming the cosine, but it's not just cosine of x, it's cosine of 4x. So basically, derivative of sine is cosine, so derivative of sine of 4x is cosine of 4x, but you also have to multiply it by this extra factor, 4, that comes from the derivative of the 4x. Okay, so derivative of sine 4x is 4 cosine 4x. Similarly, if we take the derivative of tangent of 5x, this is going to be equal to 5 times, correct, James? Derivative of tangent, which you have to remember is secant squared of 5x, right? Again, here, this 5x becomes the 5, and the tangent is becoming the secant squared. This is how the chain rule works. So you can go back and review that if you want to. And so now what we get is that this is equal to the limit as x approaches 0 of 4 cosine of 4x over 5 secant squared of 5x. But now what happens if we just try to plug in 0? Because these things are continuous functions, I can just write this as 4 cosine of 0 divided by 5 secant squared of 0. Right? This is what happens when we plug in over here x equals 0. And now what's cosine of 0? Cosine of 0 is what? I'll answer, right? Cosine of 0 is 1. And secant is 1 over cosine, so that's also 1. So this is 4 times 1 divided by 5 times 1 squared, and that's 4/5. Okay. So with L'Hopital's rule, we can just evaluate this limit, and it's 4/5, and it's a relatively simple computation. We don't have to do any elaborate trigonometry. We do need to know a few things, right? We do need to know how to do the chain rule. We do need to know how to take derivatives of trig functions. And we do need to know that cosine of 0 is 1, and secant, which is just 1 over cosine of 0, is thus 1 over 1, which is also 1. Maybe I'll put that as an aside over here, right? Cosine of 0 is 1, and secant of 0 is equal to 1 over cosine of 0, which is equal to 1 over 1, which is 1, right? So in this case, both cosine of 0 and secant of 0 come out to be 1. Okay? Yeah, I mean, you can join using your computer if that works. Okay. All right. So any questions about this problem here? Okay. All right. No questions. So let's move on. Okay. So remember, these are the three topics from last time. We had tangent line approximations, Newton's method, and L'Hopital's rule for limits. So today we're only going to do one topic, but it's a very important topic. So we'll spend a good amount of time on it. So we've talked a lot about derivatives this year, right? We've talked about differentiating functions. So I give you a function, you try to find the derivative. Okay? So it's also possible to ask the opposite question. So if we have a function f, can we find a function capital F whose derivative is lowercase f? So it's kind of finding a reverse derivative, or what we call an antiderivative. Instead of taking the derivative, you're trying to invert that process. You're trying to find some other function whose derivative is your function. Okay? And this process is called antidifferentiation or integration. So for the textbook, it's in chapter 3.7. And I would say just over here, this f of x is called an antiderivative of f of x, of little f of x. Right? So if we have a function little f of x, to find some other function whose derivative is little f of x, that other function is called an antiderivative. So we're going to spend a little time today talking about, basic ways of finding antiderivatives. And then we're going to talk about what the antiderivatives have to do with motion in physics. Okay, that's going to be our main application for today, is to use them to talk about gravitational motion in physics. Okay. And any questions about just the basic idea here? We have a function and we're trying to find its antiderivative. We're trying to find something whose derivative is that function. Give me 1 second. 1 second. Okay. Okay, great. Okay, so let's first just do some examples. Let's try to compute some examples. So we want to find antiderivatives for the following functions. So 3x squared, 6x squared, 4x cubed, and 3x squared plus 4x cubed. So let me just write these functions here. 6x squared, 4x cubed, and here 3x squared plus 4x cubed. Okay? So this we're just going to do by guessing. So off the top of your head, can you think of a function whose derivative is 3x squared? So can you think of a function that when you take the derivative, you get 3x squared? And the answer
Yeah.
is, the hint is this should be simple.
Yeah.
Yeah, Abraham?
F is x raised to the
Mm-hmm.
third power. X raised
Exactly.
to the third power.
Perfect. X raised to the third power, right? We just can guess this, basically, right? We know, well, x to the third. If you take the derivative, you get 3x squared, right? So we answer this question basically by guessing. We just say, oh, yeah, it looks like it's x to the third. But of course, there's other answers also. Another answer is you could take x to the third plus 1, right? I mean, if I take the derivative of 1, that's equal to 0, right? So x to the third plus 1 also has 3x squared as its derivative. And then there's nothing special about plus 1. It could be x to the third minus 1, or x to the third plus 75, or whatever, right? You can add or subtract any constant, and it's not going to change the derivative. So in fact, the way that we write this, if we want to look at all of the antiderivatives, we write x to the third plus c, where this c just represents an arbitrary constant. Okay, so basically anything of the form x to the third plus c is going to have 3x squared as its derivative, because the x cubed will become 3x squared, and the c disappears when you take the derivative. So you end up with just 3x squared. So if you want all the answers, they're all going to be of the form x cubed and then plus c. What becomes of the 3 and the 2? So the point is, we remember from the power rule, what's the derivative of x cubed? The derivative of x cubed is you bring down the 3, and then it becomes a 2, right? So when we take the derivative of x cubed, we get 3x squared. And that's exactly what the question is asking. It's not saying do something to 3x squared. It's saying, can you find a function that when you take its derivative, you happen to end up with 3x squared? Um, no, this looks wrong. Oh, you're looking for all of the problems. Yes, yes, yes. Okay, fine. Yes. Um, okay. This looks like a bit of an AI answer here, but in any case, all right, yeah, yes. We'll go through them one by one, but yeah, these answers do look correct. Okay. So, all right, so that's it's not like asking what happened to the 3 and the 2 is not really the right question. The right question is just, you have x cubed, and when you take the derivative, you get 3x squared. So it's the right answer, right? It's something that gives you the 3 and the 2 when you take the derivative. Is that okay? Okay. So now let's change it up a little bit. We know that the derivative of x cubed is 3x squared. Then what's something that you could have whose derivative is going to be 6x squared? So x cubed gave you 3x squared. Now you have 6x squared, which is twice as much as 3x squared. So instead of x cubed, what should we use here?
You should use 3x cubed.
Uh, Careful. We want to multiply by 2, right? So we want to use 2x cubed. Unless I may have misheard you. Maybe you said 2. Okay. So,
Yeah,
right,
2x cubed.
2x cubed, exactly, right? Because again, here we have that the derivative of f prime of x is going to be 2 times 3x squared, which is equal to 6x squared, which is what we want, right? So we take something with a known antiderivative. We know that the antiderivative of 3x squared is x cubed. So the antiderivative of something that's twice as much is going to be the function that's twice as much. Or another way of saying that is that if you multiply a function by 2, then you multiply its antiderivative by 2 also. Okay? And again, you can always have a constant. So really what you should be saying is, and I'll box these, so x cubed plus c. Over here, really what you should be saying is 2x cubed plus c. Right? You can always add what's called a constant of integration. It's just this arbitrary constant that's going to disappear when you take the derivative. Okay. Is that okay, the 6x squared? It's just going to be 2x cubed. And we guess it by saying, oh, you doubled the function, you're going to have to double the antiderivative also. Okay, so what about 4x cubed over here? So this is going to be a different question. We're not going to get it from these two. But 4x cubed, we can answer pretty similarly to 3x squared, right? X to the fourth plus 5, or in general, any x to the fourth plus a constant, right? So here we're going to get that the antiderivative is x to the fourth plus a constant, whatever that constant is. You can write 5, or you can write anything else, right? And again, this is basically just from guessing. There's no method here. We just say, oh, 4x cubed. We remember if you take the derivative of x to the fourth, you're going to get 4x cubed. That's what happens when you bring the 4 down and you're left with a 3. Okay. And now lastly, 3x squared plus 4x cubed. Well, we know that taking the derivative of x cubed gives us 3x squared. Taking the derivative of x to the fourth gives us 4x cubed. So what derivative is going to give us 3x squared plus 4x cubed? So Princeton wrote it exactly right. We're going to have x cubed, sorry, right in blue. We're going to have f of x equals x cubed plus x to the fourth. And you wrote two c's, but usually we just collect all the c's at the end. We just write one c at the end. Whatever you do, you have one constant of integration. So exactly right. Right? So when we add two functions, we can take their antiderivative separately and add them also. This is called the addition rule for antiderivatives. And it's clear, right? Because adding these two things, you take the derivative. The derivative of this is 3x squared, and the derivative of this is 4x cubed, right? So yeah, so that's perfect. That's how this works. Okay, so any questions about these examples? I mean, at this stage of doing antiderivatives, it's mostly just guessing. Although we'll talk in a little bit about some rules that you can use. But for now, you can basically just guess these answers. Okay, so let's move on. So what's one of the rules? So let's actually talk about a rule. So the first major rule in differentiation is what we're going to call the power rule. And that says if you want to take the antiderivative of x to the n, then what you get is 1 over n plus 1 times x to the n plus 1 plus c. Right? Let's check this rule. If I take the derivative, to the way I check an anti-differentiation rule is I should take the derivative of this and I should get x to the n. So let's check. If I take the derivative of 1 over n plus 1 times x to the n plus 1 plus c, I get, well, I'm going to have 1 over n plus 1. That's just along for the ride. Here, the n plus 1 comes down, so it's times n plus 1. And then the x to the n plus 1, that decreases by 1 by the power rule. So we just have x to the n, right? X to the n plus 1 becomes n plus 1 x to the n. And then the c just disappears. That just becomes 0. And now we see that this simplifies to x to the n, right? So this is good. right? So this is exactly the formula that we would get when if you take the derivative of this, then you win, then this works, right? Now, notice I say this works for every n, except there's a special n for which it doesn't work, and that's the value -1. So if you're trying to take an antiderivative of x to the -1, turns out that that doesn't really work because what would the formula give in this case? Formula would give 1 over -1 plus 1 times x to the -1 plus 1, which would be x to the 0 over 0. And this is undefined. Okay, so we're going to need another formula for when it comes to n equals -1 that we're not going to do today. That's going to involve logarithms. Okay, for now, we just won't do x to the -1. But the power rule works for everything else. Okay, because if you try to use this formula for -1, you end up getting a 0 in the denominator, and that's no good. Okay.
Do you ask a question?
Is there a question?
I'm asking if you asked a question because my line was sticking.
Oh, no, sorry. No, I didn't ask a question. I'm just saying this doesn't work because if you try to use n equals -1 in the formula, then you get something that doesn't make any sense. You get x to the 0 over 0.
All right, thank you.
All right, so this is your power rule. So now you can use this. So for instance, antiderivative. So just examples, antiderivative of, x to the 7th, you just write in the formula. It's just 1/8 x to the 8th plus c. Antiderivative of x to the 3.5 is just 1 over 4.5 times x to the 4.5 plus c, etc. Right? So it works. This works fine as long as you're not doing the antiderivative of x to the -1. Anything else is fine. Okay? So this is our first formula for antidifferentiation. Okay, or what's called integration. Okay, if you have just a simple monomial, then you just take the antiderivative by just raising the exponent by 1 and putting 1 over that new exponent as a coefficient, right? So what you see is differentiation reduces the exponent by 1. Antidifferentiation raises the exponent by 1. Okay. All right, any questions on this power rule, how this works? You should think of this as exactly the reverse of the power rule for derivatives. Okay. So another example, let's find an antiderivative. So we can say for derivative is decrease of power. Y is antiderivative, the increase of power. I mean, so the answer to y is basically that this formula works, right? If you increase the power, you're asking what function, when you take the derivative, will get you back to x to the n? Well, you want to take the derivative and get x to the n. We know that taking the derivative decreases the power by 1. So the thing that you need to take the derivative of has to have the power 1 bigger, because you know that when you take the derivative, it's going to decrease that power back to n, right? So you just check when you take the derivative of this expression, you end up with x to the n, because this has power 1 bigger. Taking its derivative makes it 1 smaller. That gets you back to n. Okay, so I mean, the proof of the power rule is literally just the check, right? You just say, oh, well, when I take the derivative of this, it works. It's x to the n. So you need to maybe think a little bit about how you derive a formula, like how you'd figure this out. But once it's given to you, the reason it works is just because it works. You take the derivative and it works. So you should think of differentiation and anti-differentiation as reverse processes. So if differentiation is going to lower your exponent by 1, anti-differentiation is going to raise it by 1. Okay? That's why it goes up. Okay, derivatives decrease of power, antiderivative is increase. Okay, so let's try a couple more examples. So let's find an antiderivative of x squared minus 3x to the 6th. And well, what we've learned is that we should do these in separate pieces, right? So x squared, we can just use our power rule. that we have from the previous page, which says raise the exponent by 1 and then also put that in the denominator. So in this case, x squared is going to be 1/3 x cubed, right? Because we raised the power by 1 and we also put it in the denominator, so x cubed over 3. Now, what about 3x to the 6th? Well, I know that x to the 6th alone would be x to the 7th times 1/7. And then the 3 just kind of stays along for the ride, right? If I know that the derivative of 1/7 x to the 7th is going to be x to the 6th, what's the derivative of 3 times 1/7 times x to the 7th? Well, it's going to be 3 times x to the 6th. And now this minus sign also just comes along for the ride. We're going to have a minus here. Okay, and so if we want to simplify this, this is 1/3 x cubed minus 3/7 x to the 7th. And if I want to, I can say plus c. Although the question just asked for an antiderivative, so it's okay to leave off the c because you want just some antiderivative. Let's check. So this is the answer, but let's check. So the derivative of 1/3 x cubed minus 3/7 x to the 7th plus c is equal to, well, it's 1/3 times the derivative of x cubed, which is 3x squared, minus 3/7 times the derivative of x to the 7th, which is 7x to the 6th, and then plus the derivative of c, which is 0. And this simplifies to x squared minus 3x to the 6th. So the check works. Okay. Yeah. Yeah. So this works exactly right. Perfect. Yeah. So this is exactly, actually, it shows the steps. James, what program is this that does this? This is good. Do you know what this app is? Um, Sorry, yes. So the software, I use something called GoodNotes. That's what I use to write. It's GoodNotes with an iPad. Um, so it's and a stylus. But actually, James, I'm curious what you're using for this, actually. This seems like a good kind of calculus teaching tool, that it doesn't just solve the problems, but it tells you how they're being solved. So I'd be interested to know what app this is also. All right. Yeah, so the app that I use is called GoodNotes. Okay, so is everybody okay with this example? You just use the power rule and you subtract the different parts and you multiply by constants when you need to. And that gives you x squared gives you 1/3 x cubed, and x to the 6th gives you 1/7 x to the 7th, and then you need to keep the 3 and you need to keep the minus sign. Any questions on this? Okay, let me state this as a general rule. So we have the power rule and then the other basic rules, which are exactly the same as the basic rules we have for differentiation, are what we call the sum, difference, and constant multiple rules. So let's say we've got two functions, f of x and g of x, and they have antiderivatives capital F of x and capital G of x. Well, if you want an antiderivative of f of x plus g of x, you just use capital F of x plus capital G of x. If you want an antiderivative of f of x minus g of x, you use capital F of x minus capital G of x. And if you want an antiderivative of a constant times f of x, you just take that same constant times capital F of x. So if I know an antiderivative for f of x and I want an antiderivative for 9 times f of x, I just multiply the antiderivative times 9. So let me say that these are the analogs of the basic differentiation rules. right? And when I say the basic differentiation rules, I really mean the basic ones. I'm not talking about the chain rule and the product rule and the quotient rule and trig functions. Those are hard rules. I just mean the basic things that if I add two functions and I want to take the derivative, I take the derivative of the first plus the derivative of the second. So it's the same for antiderivatives. If I add two functions and I want to take an antiderivative, I take the antiderivative of the first plus the antiderivative of the second. I subtract them, antiderivative of the first minus the antiderivative of the second, and if I multiply by a constant, it's just that constant times the antiderivative of the first. The analogs of the product rule and quotient rule are quite a bit harder, and you can't always do them. Okay, so I don't just have a formula for what the antiderivative of f of x times g of x is. Notice I've only done plus and minus here. You can't do times because doing the derivative of a product is hard. You have to use the product rule, and it's not quite clear how that happens, how you do that for antiderivatives. So there's something called integration by parts, which is going to show you how that works, but we're not really going to cover that. But it's in the book if you want to look at it. Okay, so these are the basic differentiation rules and the basic anti-differentiation rules. And they're logical, right? Nothing here is surprising. Okay, any questions on this? Okay, so let's do another example. So now I want to find an antiderivative of 2x to the fourth minus cosine of x, but I don't want just any antiderivative. I want an antiderivative such that f of 0 is equal to 1. Okay, so this is going to mean I need a very specific antiderivative, right? So let's start with our power rule, right? X to the fourth we know becomes x to the fifth divided by 5, or 1/5 x to the fifth. So this is going to be 1/5 times x to the fifth. And then I have the 2 here still because the 2 comes down for the ride. Now we know that minus just stays minus. Here's another one where we're just going to guess what's an antiderivative of cosine of x, meaning what's a function whose derivative is cosine of x. There's no way to really solve it. You just have to answer it, right? Sine of x, exactly. Right? So we know that the derivative of sine of x is cosine of x. So here what we have is 2 times 1/5 x to the fifth minus sine of x, because we know from this subtraction rule we can do them separately and subtract, and then always plus c. Okay? So this here is the family of all antiderivatives. Let me just rewrite this. This is 2/5 x to the fifth minus sine of x plus c. This would be the family of all antiderivatives, but we want to find a specific one, right? We want that f of 0 is equal to 1. So what we have to do is actually solve this. So let me write, so f of x is equal to this. Now we need to set f of 0 equals 1 to solve for c, right? Because we need to know it's not good enough to just write plus c. I need to know exactly which function am I going to have so that when I plug in 0, I get 1. So let's solve this for c, right? When I say solving f of 0 equals 1, right, this is really plugging in x equals 0. So this equation becomes 2/5 times 0 to the fifth, sorry, not plus, times 0 to the fifth minus sine of 0 plus c equals 1, right? This is, sorry, this here is f of 0, right? Trying to solve f of 0 equals 1. And as an equation, well, this is easy because this is 0 and this is 0. So this just becomes c equals 1, right? So this here is equal to 0 and this here is equal to 0. So what you're left with is just the C to get 1. Okay, so the final answer, so this tells us that C has to be equal to 1. So the final answer is f of x equals 2/5 x to the fifth minus sine of x. And now not just plus C, but we figured out exactly what the C has to be. So plus 1. So this is the final answer over here. Okay, so maybe if I do it in steps, this is step 1, which is find the general antiderivative. Then over here, step 2 is solve for C. You're given some condition over here, which is going to allow you to solve for what your actual constant C needs to be. And then step 3 is write down final answer. Right, and this final answer is just going to be your function that you started with, the general antiderivative with the correct solution for C over here. So in this case, we get 2/5 x to the fifth minus sine of x plus 1. All right. Any questions on this example? What becomes of the 1 if we have f of 0 equals 1? Ah, right. Well, this is the 1, right? So this is exactly the equation we're solving, right? This side is the f, we're trying to solve f of 0 equals 1. This side is the f of 0. We plug in 0 for f. This side is the 1. And then we do this to try to solve for C. So the point is when we plug everything in with f of 0 equals 1, this reduces to C equals 1. So it tells us exactly what the C needs to be. Now that you know what the C is, you just go back to your original answer and say, all right, I'm going to put a 1 in instead of the C here. All right. Does that make sense? Okay, good. Other questions? Okay, so we can find antiderivatives in general, but we can also find them subject to a condition that you need, some particular value when you punch it in should be equal to some other value. Okay, so what's the point of all this? Well, it turns out that antidifferentiation has lots and lots and lots of applications, but we're going to talk about one of them today for physics. Okay, so let's recall that when we started doing calculus, we talked about the derivative as having two interpretations. One was this tangent line interpretation, and the other one was this velocity. And so this is something that we did back in the fall. We saw that if a particle's position function is given by s of t, then its velocity, we call it v of t, is equal to the derivative of the position function. Right? So we saw that the velocity is the derivative of the position, and the way we thought of this is that velocity is equal to the rate of change of position. Right? And we also have that the acceleration is the rate of change of the velocity, right? That's what acceleration means. It's the rate of change of velocity. So a of t is the rate of change of velocity. And we know that velocity is the rate of change of position. It's the derivative of position. So the acceleration is actually the second derivative of the position, right? Because if you have position, if you take one derivative, you get the velocity. And then if you take another derivative, you get the acceleration. So here this says acceleration equals rate of change of the velocity. Okay. So the idea is, what does this help you? We know that by taking derivatives, we can get from the position to the velocity and then from the velocity to the acceleration. If we want to go the opposite way, then we need to take antiderivatives, right? So using anti-differentiation, we can reverse this process that if we're given the acceleration function, we can use that to determine the velocity and determine the position, right? Because to go backwards is to do anti-differentiation. And this is particularly useful in physics modeling because a physical system is usually governed by forces, so gravity or electromagnetism or tension, something like this. And forces we know through Newton's law, right? Newton's law, force equals mass times acceleration. If you understand the force, then what that's really telling you is something about acceleration. So when you're modeling a physical system, usually what you know is the acceleration because you know something about the forces at play. And what you want is you want to actually understand, how is this thing going to move? How's the particle going to move given the forces on it? And that means you need to convert acceleration into its position. And in particular, you do that in two steps. You convert acceleration back to velocity, and then you convert that back to position. And you have to do that using anti-differentiation. Okay? So this is going to be this application that we're going to see today. Why would you want to take antiderivatives? Well, antiderivatives help you turn information about acceleration into information about position. First, you get a little bit about velocity, and then you get information about position. Okay? So more specifically, if we're given an acceleration function, a of t, first you can determine the velocity function by taking an antiderivative of a of t, right? I mean, we have that acceleration is the derivative of velocity. That means velocity is the antiderivative of acceleration. Goes in reverse, right? So you first determine the velocity function by taking an antiderivative of the acceleration. Usually there's going to be other information in the problem that will tell you exactly which is the correct antiderivative to do, right? Just like in the previous problem when we had f of 0 equals 1. There's going to be some physical constraint in the problem to understand what to do. And then, since we've determined the velocity function, we can take a further antiderivative to determine the position function. And again, there should be something in the problem that tells you how to know which is the right antiderivative to do. Okay? So you can go from acceleration to velocity, and then you can go from velocity to position, and both of these are accomplished by taking an antiderivative. Okay. All right. So we'll close today by doing a problem on this. But before we do a problem, any questions just about the concept of how this works? Okay, great. So let's do an actual problem. So a ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. Find the height above the ground t seconds later. When does it reach its maximum height? And when does it hit the ground? And we note that acceleration due to gravity is all on the surface of the Earth is always 32 feet per second squared downward. And we're assuming, no air resistance or anything. So, and you have something like this, we'll always draw a picture, right? So this here is 432 feet. And then you have your little person standing at the edge of the cliff who has a ball, right? And the ball is thrown upward at 48 feet per second. Okay? So taking the acceleration function of a okay, I'm not sure I understand this question. I'm saying that the acceleration function is the derivative of the velocity, always. That's what acceleration means because it's the rate of change of velocity. So if you have the acceleration function and you want to get the velocity, you've got to take an antiderivative to do that. Okay. So to go from acceleration to velocity, you take the antiderivative. Maybe I'll extend this. To get from velocity to acceleration, you take the derivative. Right? So these two processes undo each other. Okay. All right. So let's go back to our question. So the acceleration due to gravity is 32 feet per second downward. So what that means is that A of t is just a constant, which I think we'll call it negative 32. Okay. Because it's going to be downward. Okay, so we usually use negative for that, for downward. Okay. Now, maybe in order to do this, we should give some kind of coordinates over here, right? So maybe this we'll use our coordinate axis here is going to be feet above sea level. So I'm going to have this is going to be 0, this is going to be 432 up here, right? Okay, so now what's v of t? Well, we take the antiderivative. So v of t, we take an antiderivative. It's another one to guess. What is the antiderivative of minus 32? Now we're in terms of the variable t instead of x. So what's a
Minus
yep,
32t.
exactly, right? So what's a function whose derivative is minus 32? It's exactly minus 32t, right? If you take the derivative of this, you get minus 32. In fact, you could think of this as the power rule with n equals 0 if you want, but it's actually easier to just write this. So minus 32t plus c. So we need to know what is the correct antiderivative to take to actually make this work. And well, the problem tells us, right? It's that we start with a speed of 48 feet per second upward. So what that means for us is that the velocity at the original time, at time t equals 0 when we start, is actually 48. Right? This comes from the problem, right? V of 0 is 48 because it starts going 48 feet per second upward. So now we have to do our procedure to solve for c. So negative 32 times 0 plus c equals 48. And solving this for c, this gives us that c is equal to 48. So we actually get that v of t is equal to minus 32t plus 48. So that's going to be our velocity function. Eventually, we want to find our position function, right? All of these questions are about position. So we want to know, we want to go find the position function first before we can answer all these questions. So before we move on to find the position function, does anybody have any questions about how we found the velocity function?
Yeah, hello,
Yep.
Robert.
Yes, Abraham.
So the minus 32 is constant for any object that is moving downward.
Mm-hmm. Yeah, so the acceleration is constant, but the velocity will not be constant. It'll move faster as it falls further. Yeah, the minus 32 is constant because it's a constant force due to the Earth's gravity. And so that doesn't change, at least it doesn't change at, the levels that humans do things. It changes if you're, in the stratosphere, or it changes if you're on the moon, but it doesn't change on the surface of the Earth.
So that was
Mhm.
32 feet per second square is the same as 9.8 meter per second square, right?
Correct. So this question's in feet, so we're doing everything in feet.
All right.
Yeah. Okay, so let's go on. Let's find S of t. Well, this is again going to be an antiderivative. Okay, S of t is going to be the antiderivative. Here we can use the power rule. So the minus 32t, remember this is t to the 1. So the antiderivative of t to the 1 using the power rule is 1/2 t squared. Antiderivative of 48 we know is just 48t. And then we're going to get another constant c. Now, what else do we know from this? We know that at time 0, how high is the ball? We know that the ball is at 432 feet. So this is another thing to note, is that S of 0 is equal to, S of 0 has to be equal to 432, right? Because the position is at a height of 432 feet when you start. So what does this mean? Again, when we plug in t equals 0, these all just go to 0, and we're left with c. So this gives us that, negative 32 times a half, so that's negative 16, 0 squared, plus 48 times 0 plus c equals 432, which means that c is equal to 432. So your final answer for S of t is actually, well, minus 32 times 1/2, that's minus 16t squared plus 48t plus 432. Okay, so we used this information about acceleration. All that we knew is that acceleration is negative 32 due to gravity. And from taking one antiderivative and using the right one, and then taking a second antiderivative and using the right one there, we ended up with this position function. So this is telling us how the ball is going to move with time, at least until it hits the ground and it's acted on by forces other than gravity, the electromagnetic force of the ground, right? So the position function is given by this quadratic function. It's negative 16t squared plus 48t plus 432, okay? And the velocity function, which maybe I'll box also, is given by minus 32t plus 48. Okay. So now that we have these two functions, now we can answer these questions. When does it hit its maximum height? And when, so find its height above the ground t seconds later. So that's this, right? This is the first question. Right? The first question is just what is its height after t seconds? That's exactly this position function. That's 16t, negative 16t squared plus 48t plus 432. Okay. So now we want to answer the next two questions. When will it reach its maximum height? And when does it hit the ground? Okay. So I'm going to just recopy this on the next page. And then we'll answer these last two questions. Okay. Let me add a new page. Okay. So recall v of t is equal to negative 32t plus 48. And S of t is equal to negative 16t squared plus 48t plus 432. And the questions are, when does the ball reach maximum height? And when does it hit the ground? Okay. Okay. So, okay, first question. When does it hit maximum height? Well, we know that it hits the maximum height whenever this function reaches its maximum. And we know how to determine maximums of functions, right? You set the derivative equal to 0. But we already know what the derivative is. The derivative is this velocity. So the answer is going to be maximum height when v of t equals 0. Okay, so we just solve this, right? Because when the ball hits the maximum height, that's when the velocity moves from upwards to downwards. So at the moment that it hits that maximum height, the velocity is 0, right? Because it goes from positive as the ball's going upward to negative as it's going downward. So we just solve v of t equals 0. And so v of t, we have an equation for that. So it's just minus 32t plus 48 equals 0, which gives you 48 equals 32t. And that gives you that t is equal to 1.5. And I'll just add seconds because that's our units. Okay. So after 1.5 seconds, the ball is going to reach its maximum height. So maybe I'll call these question 1 and question 2. So this is answer 1. Is that okay? Question number 1? So maximum height exactly when the velocity is 0. And then you just solve because we know what the velocity function is. Okay, so let's answer question number 2. So let's do question number 2. So question number 2 over here, we want to know when does it hit the ground? Hitting the ground means the position function is 0, right? So it hits the ground. What we're really doing is solving s of t equals 0. This is what it means when the ball is on the ground. Okay, so let's see what happens. We're solving negative 16t squared plus 48t plus 432 equals 0. Turns out that you can just divide this by negative 16. This is so if you just divide everything by negative 16, this is going to give you that t squared minus 3t, and then 432, that's 320. Yeah, so that's going to be minus 27 equals 0. Okay. And so this is not actually going to factor, so I'll just use the quadratic formula. What does the quadratic formula say? This gives us that t is equal to 3 plus or minus the square root of b squared, so that's 9, minus 4ac, so minus 4 times 1 times 27 over 2. And I don't think this is going to factor. Yeah, I don't think this factors.
Hello?
Yes, hello? Yeah, Rush? I don't think this factors, right?
X will get minus 27, right?
Minus 27, yeah.
Yeah, but we put positive. That's
Well, right, all the signs change because I'm dividing by negative 16, right?
what I
So,
mean. In the radical, what I'm trying to say.
oh, well, but, oh, sorry, yes, you're right. Sorry, minus 27. Thank you. 1 times minus 27. Thank you. Okay, so this is going to be 9 plus 108, so we're going to get 117 over here divided by 2. And let's just see, what is this actually equal to? So 3 plus square root of 117 divided by 2 is, so this is just going to give us, so 6 point, so we're going to get 6.91 or negative 3.91. Yeah. Okay. But of course, this answer we have to throw away because negative time doesn't exist, right? So this is what's called sometimes an extraneous solution. Okay. So the actual answer is about 6.91 seconds later. That's when the ball's going to hit the ground. So this one is the answer. Okay. So the ball is going to hit the ground 6.91 seconds after it's thrown. Okay, and all that you're doing is algebra here. You're just setting S of t equal to 0. The calculus was all done at the beginning when we figured out what this S of t actually was. And so recalling that we had to, to find that S of t, we had to do these antiderivatives. We started with acceleration, we got velocity as an antiderivative, and then we got acceleration as another antiderivative. Okay, so it's a compound question, but this shows us how antiderivatives can take information about gravity and convert it to information about the path of a ball or a particle. Yeah, so we excuse the negative value, as Enoch says. Exactly right. This one's extraneous. It doesn't count. It doesn't tell us anything physical. Okay. Yeah, so I mean, some of the physics rules all come from they come from calculus, right? They use calculus to derive the physics rules. That's where they all come from. All right. So any questions here? I suppose I should say 6.91. We should do units, so 6.91 seconds. Okay, so I think that's a good place to stop then. So a couple of homework exercises. So first one is kind of a straightforward antiderivative. Find all antiderivatives of 4x to the 2/5 minus 5 times square root of x. Second question is another one of these type things. Find a specific antiderivative. So find an antiderivative of this function such that f of 1 equals 10. So you need to solve for c and find the right one. And then the third one is a physics problem. So you have a car traveling at 88 feet per second, which is about 60 miles an hour. And then the brakes are fully applied, and that produces a constant deceleration. That just means a negative acceleration of 22 feet per second squared. And the question is, how much distance is traveled by the car before it comes, that's spelled before it comes to a stop? Okay, so if that's how much your brakes can apply, how much distance are you going to go before you can stop, right? This is kind of thing that car makers need to understand, how powerful their brakes are, how long do cars need to stop, for safety, right? So let me just give some hint here, right? Find, V of t and S of t first. And then the idea is so step 1, then 2, solve for v of t equals 0, right? This is going to be time that the car stops. And then step 3 is use this t to find S of t, which is going to be the distance traveled. Okay, so 3 is going to be a challenging problem. And if you can't do it, that's fine. We'll go over it next time. 1 and 2 are a little bit easier, so I certainly encourage you to try 1 and 2 and to try 3 if you want a bit more of a challenge. And, as a kind of application of this, antiderivatives. Okay, and so I'll send this all out as usual. Oh, that should say antiderivative, another little typo there. So thank you for your attention. So next week we'll meet. Number 3 is not so bad, but for people seeing this for the first time, there's a few things that you have to do. Okay, so thank you for your attention. So on March 27th next week, we're going to discuss the other meaning of antiderivatives, which is the relationship between antiderivatives and areas. So today we talked about antiderivatives and how they relate to motion. Next week we'll talk about antiderivatives and how they relate to areas. Okay, so that'll be our topic. All right, any questions? And also, if you haven't put your name in the chat, please type it in now so we know that you attended.
Yeah, hello, Andrew.
Hi, AB, how are you?
I want to tell the teacher sorry for receiving that method late, And next time, I think the distributor said that she was going to start by 3:30. But then I will tell her this straight to start by 3 o'clock. Then she can be able to distribute the data sooner. Ask all the teachers sorry for receiving your data later.
Mhm.
So let us continue coming to class to see how best we can end this particular class. Okay. Thank you for the class today.
All right. Thank you. Sorry, I need to just get a phone
Hello,
call.
boy.
Yeah, hold
Hello.
on. Yeah, sorry. Hold on. Let me just get my screen back up. Give me a second. What am I doing? Let me get my screen back up here. Yes. Hi, Rush.
Yeah, it's Enoch.
Oh, Enoch. Hi.
Yeah, something I wanted to say. This anti-derivative, it will also introduce to actually integrate or find the area under the curve, right? For example, when you are given the volume of the sphere, the volume of the cone, you can also use this as a simple method to find the area under the curve.
Yeah. This is what we're going to be doing next week. Yeah. So we're going to be talking about the relationship between antiderivatives and areas.
Okay, sure.
All right. Other questions?
Also,
Yeah.
hello.
Hello. Yes.
Tell about name in right?
Rush. Yes.
Okay.
Hello.
Okay.
You okay. Okay. Let me stop the recording now.